Here, I try to give you a sense of what a pixel is and how the three primary colors combine to give us sensory fluctuations in terms of the color. All right, and color is not intensity. Color is not hue, is not intensity, and yeah. So there's a whole science of it to discuss about colors, but we're not there, right? So if you're interested, read up more about colors from the Pillow library and signal processing pages, a lot of them. But here what we want to show is how do the three integers in the tuple, the red, green, and blue, form so many different colors, right? So the idea is this, that you can think about an image, the one that we were sharing, like here, right? So an image like the right hand side, when it gets loaded into computer memory, will appear like this. All right, so the top left pixel will be represented by this pixel, the second pixel next to it, then the third pixel next to it, and so on. So it'll be loaded like this. Then each pixel will have a combination of three numbers, right? Remember the tuple of RGB. So how do we get all these brilliant colors like, yellow mangoes and oranges and red apples and orange t-shirt like that? How do we get those? So it's all a combination of three primary colors of different intensities. Okay, so we can set red color to full red here, all right? Imagine there are three planes and you can set the red plane, green plane, and blue plane, right? You can set the pixel on the red plane 00 as full red, black for the green plane, and black for, that means no green color, no blue color for the blue plane. So once the hardware scans across, it combines these three integers and produces pure red for our eyes. This is how we see a pure red. Now let's look at the so the same goes for the green and the blue. All right, and we can see that if you draw a line from x comma y, right? So 1 comma 0 across black, green, black. So we see a green. Black, black, green, black, black, blue, we see a blue. Now what about other colors? The immediate secondary colors, that means when we mix only fully powered two primary colors, such as this, right? No red, full green, and full blue, we will get cyan. What if we have full red, full green, and no blue, yellow? And full red and full blue, no green, pink or violet. All right. So again, different shades, such as different intensities of each color, will produce variations of that color. So as I gave an example earlier on, if we reduce the red color to half or 3/4%, 75%, we might get a sort of a blood red color, maroon color in that sense. Now, how about the other three important colors: black, white, and gray? Okay. So for black, for your screen to display black, all the display pixel does is to turn off the red, the green, and the blue. And then when you combine by joining a line across like this, you see a black color over here. And for white, it's the other way around. Turn on all the primary colors. A bit like rainbow, right? You combine all the 7 colors, you get white. So our white is probably not pure white, but white enough for us to think about it as white. Again, the science of color, really fascinating. Not what we are trying to discuss here, right? But to sort of simulate white, you just turn on 255, 255, 255. Or in hexadecimal, hex, FF, FF, FF. And that's a very easy combination to remember. Now, what makes a pixel gray? And this is interesting. We see gray and when we can say that that's gray. And some of us would debate a little bit. No, that's bluish gray. No, that's reddish gray, right? So how does one compute or equal to, right? How does one check whether a color is gray? Very simple. Just look at all the integer values of the tuple of primary colors. So long as they're all equal to whatever. For example, if they're all equal to 128, which is half of 255, right? So 128, 128, 128, you get a pure middle shaded gray. Like it is exactly halfway between black and white. You might not agree because it seems like more whitish than darkish, right? This gray. But by programming, by definition, by construction, we all know that this is exactly 128, 128, 128. So yeah, definitely it's 50%. Okay, so this is how we get gray. How does one test whether it's gray? Check whether pixels 3 color components are all equal. So white is one form of gray because it's all equal to 255. And black is the sort of darkest gray because it's all 0 equals to 0 equals to 0. Okay, great. So that gives us a sort of quick intro into how various colors are formed. Next, very quickly, we want to be able to load images, see image on the screen, and save image, right? So how do we grab the image file from the hard disk? Very simple. Just simply say, first of all, you must import the pillow library. Okay, so import the pillow library. The pillow library contains several very useful sub-libraries. So here, the image is the core of it. So with the capital I, image as a sort of a storage content from pillow, then we can work on this image object and then derive various interesting modifications from that. So import image and we alias it as img, and that's up to you. So and then simply just say img.open. That file name will do. Finish. When you say open, unlike Python's file open, but that doesn't mean it reads. You have to sort of say fs.read, then you read, right? So this is a little bit different from that. When you open, you're done. When you open, the whole image is read in because Pillow figures that why would you want to open and not do anything, right? So whenever you dot open it, okay, the entire content of this image can be assumed to have been loaded into this variable called img1. Okay, so remember what's a variable? It has a name called img1, but it's essentially a container for a Python object. What is this Python object? It has got a type of Pillow's image. The full name is PIL dot capital I MAG. So pill dot image. So the type is this. And when we say a dot show, we see this new window, literally a new window being popped up and shown to us. Okay, so then we verify that, yeah, this is the right image file that we want to work on. Okay, so this shows an independent window of the picture. And actually this dot show here sort of activates your operating system, whether it's Mac or Windows, to run another program to show. So your Python program continues. That's why I want to put in the comment here. Your Python program continues on. Once it's shown, it doesn't get hung there until you close the window and then it continues. But rather, it shows and then it continues. So keep yourself aware of that point. And then we start to query some properties from this image, like what is your format? Are you a JPEG file, GIF file? You know what is that? So img1.format gives us a string, which is quite readily self-explanatory. Now, whether it's JPEG or GIF or whatnot, it can be converted internally as a different representation format. Very commonly, we would want it to be in RGB format. Now, in the earlier days when memories were very expensive and therefore very scarce for every computer, we would try to avoid RGB as much as possible, but because it takes up a lot of space. Every pixel is one number. But nowadays, don't worry about it. Okay, just try to use RGB mode, so the mode. And we can, of course, we have to know the size of the image. How does Python program know whether I'm dealing with a thumbnail or a huge, Canon digital photo that's like 18 megabytes large, right? How do I know the size? As same as data frame dot shape, but here we say image1 dot size. Well, don't ask me why they don't use shape. Maybe it's good because shape returns row, comma, column, remember? So here size returns width, comma, height. And with comma height, again, is a convention use. Don't try to write your program that returns height comma width. It will be super confusing, very hard to document it, very hard for people to use it. Okay, so width comma height, and from there on, we are able to report it or create copies of it, or do all the relevant operations that are fitting to this width and this height. Okay, and so now we have successfully loaded in, displayed, make some queries, preliminary queries about the nature of this image. The next slide, we want to be able to save, right? And we not just want to be able to save, but we might want also to save in different file types, file formats. Maybe the recipient didn't want a JPEG, they want a PNG file. They might want a GIF file. They might want a BMP file, Windows BMP, or you might want that. So it's very simple. Both both goals, saving a file and converting, can be done using the .save, right? So you just specify the file name accordingly with the desired extension. It can be .jpeg again. It can be .png, .gif, .bmp. A lot of file formats are just supported natively by Pillow. So it's really, really powerful with very high quality retention of the image itself. So we all know that JPEG images, they are a bit lossy. So if you load and save, load and save, load and save, even set at high quality, after maybe a few hundred times, you will get very low quality, almost disgusting image from there on. Okay, so JPEG tends to be that. But with Pillow, it is able to still upkeep this lossy algorithm. So it's pretty good in that sense, as in not creating distortion or loss. Okay, so by all means use it. It's quite freely available, and definitely you need a lot of these capabilities. So up to here, we've been treating images like basic building blocks. Just like load, show the whole image, save the whole image. So join me in the next video segment. We'll see how to slice and dice the image, almost operating the image like as if it were a data frame. Okay, so see you in the next video.